In 2002, the ministry approved the establishment of College University Kejuruteraan Utara Malaysia, KUKUM, the 17th public university in Malaysia. In 2007, KUKUM was rebranded as UNIMAP. UNIMAP offers programs of study leading to the award of diploma, bachelor's, master's and PhD degrees. Following the restructuring of the university in September 2020, UNIMAP now has 6 faculties offering more than 40 programs of study. Faculty of Electrical Engineering Technology, Faculty of Electronic Engineering Technology, Faculty of Mechanical Engineering Technology, Faculty of Chemical Engineering Technology, Faculty of Civil Engineering Technology, Faculty of Applied and Human Sciences. UNIMAP continuously carries out research that brings benefit to all. Nanotechnology research in UNIMAP looks into faster, easier and more accurate detection of microbiological diseases. The HPV-CC kit has high sensitivity that allows early detection of cervical cancer through saliva. A bus monitoring system developed by the UNIMAP Center of Excellence for Advanced Sensor Technology facilitates efficient monitoring of the movement of university buses for students. Under UNIMAP's social responsibility programs, an alternative energy source kit known as EPS kit has been developed. Each year, UNIMAP produces alumni whose presence is felt the world over, in many parts of the world.
Being graduate from UNIMAP, it really helps me in adapting to the working environment, and it helps me speeding up my learning curve. And I think the best thing about UNIMAP is they don't just teach you, they prepare you.
The soft skills, problem-solving analysis, as well as a lot of hands-on practical that we practice in lab, it will help the graduates to be more confident when they graduated later on.
UNIMAP researchers are globally recognized, evident through the acquisition of numerous international grants.
UNIMAP is my first choice because the programs offered here are focused and they fulfill the expectation of the industry.
Apart from academic and research, which are the university core business, sport, culture and volunteerism are also given due to the attention. It's up to the student to choose which field he or she wants to immerse into.
The success and achievements thus far have placed UNIMAP on the world stage.
human mind. With its 6.4 feet primary mirror and 4 powerful science instruments, it will study the first stars and galaxies, atmospheres of extrasolar planets, and learn where elements that form life came from, and much more. Webb is a successor to the iconic Hubble Space Telescope, which operates in the ultraviolet, visible, and near-infrared, and of the Spitzer Telescope, which operated in the near and far infrared. And it is complementary to the Chandra Space Telescope, which observes in the X-rays. Now, you might ask, why launch telescopes in space? And the reason is that the light which reaches the Earth is filtered through its atmosphere. And even that which reaches us is blurred. So, but when we have telescopes in space, they can collect all the wavelengths that is required to study the cosmos. By looking at different wavelengths, we get different aspects, and this expands our view of the universe. Here are a few examples. On the top left-hand corner is an image of the Crab Nebula taken by the Chandra X-ray telescope. And the X-ray goes right through to the heart of the nebula and allows us to see details around the central pulsar. And about 20 years of observations of this object with Chandra have enabled us to see the motion of particles in the bright ring. This nebula was first observed by the Chinese in 1054, who thought it was a bright star, but it turned out to be, we know now, a supernova explosion, and it's now supernova remnant. The image on the top right-hand side is a Spitzer image in the infrared of the star Zeta Ophiuchi. And the infrared goes right through the dust, and we can see the star behind the dust, and we're able to learn that there are powerful winds from the star, which cause ripples in the dust and create a bow shock. The lower left-hand corner is an image of the Ring Nebula taken by the Hubble Space Telescope, which shows a lot more details of this nebula, which are the gaseous layers of a dying star. On the lower right-hand corner is a composite image of Chandra, Spitzer, and Hubble of 2 interacting galaxies, the antennae galaxies. And from the individual images, we can learn a lot about not only the interaction, but the whole life cycle of massive stars, right from birth to the death as a compact object, giving off X-rays. Okay, so we just saw some objects which were close to Earth. But what do objects look far away into space as we stare deeper into space? This is an image from the Hubble Space Telescope called the Hubble Ultra Deep Field. It has about 10,000 galaxies going back in time to a few 100 years, a few 100 million years after the birth of the universe. So this just gives us a glimpse of the distant universe. With now the light arriving on Earth from the farthest objects in the universe left those objects billions of years ago. So we are really looking back in time. We see these objects not as they're today, but as they appeared a long time ago. The universe itself started when a singularity, which is a really tiny point, contained the entire mass and energy of the universe, and that suddenly started expanding. And this is a phenomenon the scientists call the Big Bang. There wasn't really a big, loud sound, but because of the sudden expansion, they've named it the Big Bang. Now, as the universe expands, the light in the universe stretches to longer wavelengths, and this is called the cosmological redshift. So the light that started off from the first stars and galaxies in the ultraviolet or visible has now stretched all the way to the infrared. And so this redshifted light is what will be observed by the Webb telescope. And that is how Webb will look back in time and be able to see the first stars and galaxies. Webb can also peer through and examine dust because of the infrared light. Here are three images. The one on the left is a Hubble image in the visible. The middle one is the Hubble image in the infrared. And the right one is a Spitzer image in the mid-infrared. Now we can see that the visible image has these big dust, pillars of dust in the Eagle Nebula, and the stars forming behind those cannot be seen because the visible light is absorbed by the dust. But in the middle image, the infrared light is able to penetrate the dust, and we are able to see the stars. And in the mid-infrared light, the decaying pillars are seen in infrared from the bright light of the newly formed stars. So Webb specializes in the infrared. So just remind ourselves what the spectrum looks like. So on the left-hand side, we start with the shortest and most energetic waves called which are the gamma rays. And on the extreme right are the long wavelength, low energy radio waves. And the visible part of the spectrum, which is the part we see, which is marked like a rainbow in the middle, is really very small. And so if we want, and the part of the spectrum with wavelength longer than red is known as the infrared. And so we have to see that with telescopes. And the Webb telescope, it operates in the wavelength, which goes from 600 to about 28,800 nanometers. So let's remind ourselves about the history of the universe. As I said earlier, it started with a Big Bang, and then it suddenly started expanding. And as it expanded, it cooled down, and particles started to form. Particles of ordinary matter started to form. And the protons and neutrons and electrons were formed, and a few 100 million years after that, these stars were formed. The electrons and protons had combined to form neutral hydrogen atom, and the neutral hydrogen atom started forming clumps. They were drawn together by gravity to form clumps, and as the clumps of gas condensed, nuclear reaction took place and stars started forming. This period in between, the gas was mainly opaque to light, and the astronomers call that period the Dark Ages. After the stars were formed, they started ionizing the neutral hydrogen, and that period is known as, by the astronomers call it, the reionization period. And gradually the stars started combining together to form galaxies, and the universe gradually became the transparent universe we see today. So the Webb, what Webb will do, it will study the early universe. Its infrared observation will help create the first detailed snapshot of galaxies in the early universe and provide more information than ever before. The new data will allow analysis of individual objects to understand how the surrounding gas changed from neutral to ionized, creating the transparent universe we see today. Webb will discover some of the first galaxies. In this image from the Hubble Space Telescope, the inset shows a galaxy which is about 400 million years after the birth of the universe. And as you can see, that it's a very irregular shaped galaxy. So the giving us some idea of what the earliest galaxies look like. Webb will see far more infant galaxies like this. So whereas Hubble, we can think of that it saw toddler galaxies, Webb will see baby galaxies. So here is what I will call a flip book of galaxies over time. And here, these are images taken by current telescopes, which go back in time and give you some idea of how galaxies evolved over time. And Webb will examine these early galaxies and eras that followed in new detail. And it will provide us essential insight and help us learn more about how galaxies evolved. We know that galaxies change over time, and we can see that in this flip book over here. And we know that they grow, collide, and merge into each other. And Webb will give us a lot more information on this. Here is an example of how one of Webb's instruments will do these observations. So there is the near-infrared spectrograph, which is a multi-object spectrograph. And this will have a huge impact on galaxy evolution science, because it has something called a micro-shutter array, which are lots of little tiny windows, which can be open and shut to do the observations that astronomers want to do. And because of the number of micro shutters, this instrument is capable of taking about 100 sources or more at a time. So you can get spectra of a lot of sources at one time, and you can see the spectra of galaxies from now till about 200 million years after the Big Bang. So here are examples of two simulated spectra that this spectrograph will take. Webb will also be able to dissect black holes and give us more knowledge about black holes, not only not only about the black holes around our own galaxy, called Sagittarius A, but also distant black holes. So in nearby galaxies, Webb will take high-resolution spectra to learn about the temperatures, speeds, and compositions of materials at their centers. This data will be used to measure the mass of black holes at the center of galaxies by mapping speeds of the central gas and stars. Webb will study the feedback loop between central black holes, their powerful jets, and the formation of new stars in those galaxies. Webb could address broader questions of how galaxies form, including which came first, the galaxy or black hole. Webb will also re-examine how stars form, live, and die. Here are two images of the Eta Carina Nebula taken by Hubble Space Telescope. On the left is a visible light image, and on the right is an infrared light image. So as we saw earlier, the visible image has a lot of dust, which is hiding the stars behind it, whereas the infrared light shows us stars forming in those dusty regions. The Webb's view of star formation will show us even more details of star forming regions than we saw in the Webb images. Its images and data will help us learn about the physical and chemical properties of stellar and planetary systems. It will also give us insight into their formation. Webb will also detect molecules in star-forming regions like this one in the small Magellanic Clouds. Webb will capture spectacular infrared images of space, but its real power is in spectroscopy. Spectroscopy is a scientific method for studying objects and materials based on detailed patterns of colors or wavelengths. So spectrum, as you know, is the breaking up of the light into its component colors. Astronomers will use spectra captured by Webb to study mature stars of different size, mass, age, color, temperature, evolutionary stage, and formation environment. It will study newly forming stars cocooned in dense dark clouds of gas and dust, cold molecular clouds that collapse to form stars, gas and dust ejected from dying stars, and molecules between stars. It will also re-examine our own solar system's planets. Here is an image of Jupiter in the infrared. Webb will observe the solar systems from our solar system from Mars and beyond, giving us greater details of the planets and of their atmospheres. And it will also go beyond our planets into the Kuiper Belt objects. And that will help us learn how our own planetary system was formed. The image on the left is that of Jupiter's moon Europa, and we can see that there are signs of oceans, ice sheets, warm water geysers on it. Webb will be able to look at it in more detail and tell us more about the surface of Europa. The right-hand image is a map of the surface of Titan, which is the moon of the planet Saturn. And this has clouds, hydrocarbon rain, lakes, rivers, craters, dunes, weather, ice rocks, and we will get much more details of this when we go back there with observations of Webb. So Webb will be able to study the surfaces and atmospheres of the planets in our own planetary system, in our own solar system.
Dr. Hasan?
Yes.
Yeah. In your past 3-4 slides, you keep mentioning dust. How important is this dust for space science, for observing telescopes and all that, and how does James Webb help in this?
So the universe is actually filled with quite a lot of dust, and the new stars are cocooned in this dust. They're buried in this dust, and we can't see them. We can't see. If we only observe in visible light, we cannot see them because the visible light gets absorbed by the dust. But the infrared light from those stars penetrates through the dust. So the cooler stars, which send out infrared light, that goes through the dust. And since Webb observes infrared light, it is able to see those stars. And even on Hubble, the infrared instrument on Hubble is able to see it, but it's not as powerful as Webb. So Webb will be able to see far more stars and far more details of those star-forming regions. Okay. So, so infrared light also helps us find distant planets, because planets are cooler and they are very bright in infrared light, whereas the host stars that they orbit are hot and do not emit that much infrared light. They are fainter in infrared light than the cool planets. So because of this high contrast in the infrared, that is an ideal wavelength to look for planets, for extrasolar planets. This image on the right is a direct image of a planetary system, of an extrasolar planetary system, which was taken actually by ground-based telescopes, the Gemini telescope and the Keck telescope in Hawaii. And but Webb will be able to, because of its ability to see fine details and quick response, it will be able to see fainter and smaller planets and more distant planets around other stars. So we will be getting more information on exoplanets, and maybe even it will also look for Earth-like planets by studying their atmospheres. So, so I just mentioned that we're looking at atmospheres and it'll be decoding the atmospheres. So just to give you an example of a planetary atmosphere, the only planet we know really well is our own planet. And this is a spectrum of the atmosphere of our planet. As the sunlight goes through the atmosphere of the planet, it gets absorbed by the molecules of oxygen, water, carbon, methane. And this is the kind of spectrum that is produced. Now, each molecule has a very typical spectrum, which is, so we can think of a spectrum of molecules like fingerprints. So when you see the spectrum, you can immediately recognize that this spectrum is from molecule, say, carbon or water or methane. Of course, Webb is not going to look at the Earth's atmosphere, but this is just to give you an example of the kind of atmospheres that Webb will be looking for. So it will determine the chemistry of the exoplanets when it will observe the transits of planet at different wavelengths of light. So in this way, it can see whether there's water, carbon dioxide, methane, or any other molecule in the extrasolar planet. In fact, there are currently there are programs which are planned to observe Earth-like Earth-sized exoplanets, Neptune-sized exoplanets, and Jupiter-sized exoplanets with Webb. So how do we study atmospheres of exoplanets? This we do by studying by using a technique called transmission spectroscopy. And in fact, the spectrum I just showed you of Earth was a transmission spectrum. So Webb will observe the star spectrum, and then as the exoplanet passes in front of it, it will measure the spectrum again. And the scientists will subtract the star's light with the spectrum to see which molecules of the planet's atmosphere were absorbed. And these will appear as dips in the spectrum, as we saw in the Earth's spectrum. Webb's data will also be transformed into models or maps of exoplanets to provide more information about exoplanets at each stage of their orbit. By using both imaging and spectroscopy, Webb will be able to detect what other telescopes have not been able to. Spectroscopy helps researchers identify the colors, temperatures, motions, and masses of celestial objects, helping us to learn a lot more about distant worlds. So I have given you a little bit of an idea of the science of the telescope. Now let's look at the telescope itself. So the telescope, this project is a partnership between NASA, the European Space Agency, ESA, and the Canadian Space Agency, CSA. And the mission lead is the NASA's Goddard Space Flight Center in Maryland, which is where I live. And the prime contractor for it is Northrop Grumman Space Systems, and its facility in California is where Webb was made. It has 4 instruments: the near-infrared camera led by the University of Arizona, the near-infrared spectrograph led by the European Space Agency, and the mid-infrared instrument, which is a partnership between NASA and the European Space Agency. And then the fine guidance sensor and the near-infrared imaging spectrograph that is provided by the Canadian Space Agency. So on the right-hand side is a cartoon of the telescope, which I'm sure you have seen many times. It's a gold primary mirror, and then the secondary mirror, then and the instrument module that is called the optical telescope assembly. And below it is a sun shield, which protects it from the sun, from getting hot. And at the bottom of the slide, I've shown you the 4 science themes, just to remind you: the end of dark ages, the first light, assembly of galaxies, birth of stars, and planetary systems. It is designed to be a 5-year mission, but we expect it to go for 10 years or maybe even more, depending on how long the instruments last. But it will have enough fuel to take it for more than 10 years. Okay, so Webb is really a feat of engineering. There are a lot of very new technologies developed for Webb, but I will just mention a couple over here. One is its primary mirror, the other is the sun shield. So the primary mirror is 6.5 meters in diameter compared to Hubble's 2.4 meter mirror and Spitzer's 0.85 meter mirror. So it's a huge mirror. So why are we so excited about a huge mirror? And the reason is that in astronomy, the more light you can collect, you can think of the mirror to be like a light bucket. The more light you can collect, the fainter objects you can see. So that means the small objects nearby or objects which are so far away that they would look, that they are faint by the time the light reaches here. So we need really large mirrors to see distant objects and faint objects. But this 6.5 meter mirror is too huge to fit into a rocket. So technologies had needed to be developed to make it a folding mirror. So it is built in 18 pieces, hexagonal pieces, which fold back like an origami to be fit into the telescope. And I have some pictures later on. I had one earlier as well. And here are the other parts of the mirror. The light hits the primary mirror, then it goes to a smaller secondary mirror in front of it, and then through a hole in the primary to a tertiary mirror, and then it'll go to a fine steering mirror to adjust for vibrations before it enters the science instruments. The 18 mirror segments, as well as the secondary mirror, are made of beryllium, which is a very strong and light metal, and it doesn't change much with variations in temperature. And they have been polished to the correct shape so that when they are cold, they will get the shape that is required. So for those students who are a little more advanced and can understand ray diagrams, the image on the left is a ray diagram of the telescope. The telescope is known as an astigmat, unlike the Hubble, which is a Cassegrain telescope with a primary and secondary. The Webb has a tertiary mirror as well. And it's important for Webb to have 3 mirrors because it is the primary mirror being so huge, if it's pure spherical, it will not be able to focus all the rays into a single sharp point and give a sharp image. And the rays at the edge focus at different points. And so there are 3 major kinds of errors which get introduced with a large telescope if it isn't properly configured. So one is spherical aberration, where the rays from the edges, from the ends of the mirror focus at different points from the rays that hit in the middle part of the mirror. Then there's astigmatism, where the rays focus at different parts on the axis, leading to a coma, leading to a tail. And then the third one is astigmatism, which is again caused from the edges of the mirror. So the way that the Webb mirrors are configured, the spherical aberration, which I first mentioned, is fixed by configuring the primary mirror in such a way that there is no spherical aberration. The secondary mirror is configured to remove coma, and the tertiary mirror is configured to remove astigmatism. So the final image is then sharp. The fine steering mirror is there just to remove the vibrations of the telescope before the rays enter the instruments in the focal plane.
Dr. Hasan?
Yes.
You mentioned a fine steering mirror to remove vibrations.
Yes.
For the benefit of our younger listeners, the telescope is up there floating in 0G. How much vibration will there be?
So it's also it's not standing at one still point. It is orbiting a point called L2, and I'll be talking about it. So it will be fairly stable, but there will be small vibrations, and I don't have the exact number in my head, but they will be very small vibrations. So if we want to get really sharp images, we want to get rid of those vibrations as well. Okay, so on the top right image over here is the back side of one of those hexagonal mirror segments. And you can see there's a lot of machinery behind on those elements. And there are, at each corner of those elements, there are what are called actuators. And there's one at the center of the element. And these actuators are able to slightly change the shapes of these mirrors. And so all these 7 actuators are used to get each of the mirror segments into the correct position to focus the mirrors. So it's, as I said, this is also a very new and very fine technology. So at the bottom right-hand side it shows a picture of the telescope outside a testing chamber at NASA's Johnson Space Center in Houston, Texas. This chamber was actually built for the Apollo mission, and it was reconfigured to test the optics of the Webb telescope. We learned a lesson from Hubble, that the optics of Hubble was not tested before launch, so it was decided, but since it was in a low Earth orbit, we could send up a servicing mission, but Webb will be too far to be serviced, so we have to make sure that the optics were working. So Webb was sent to Johnson Center to test out its optics. And here it's outside the test chamber. This is just a fun picture. This is an actual picture of the Webb mirror taken in space by one of the Webb science instruments, the near-infrared camera. And this image was released by NASA on February 11. So it's just a nice picture showing, of the primary mirror selfie. NASA called it the selfie. So here is a picture of the telescope in the Northrop Grumman facility in Redondo Beach, California. And what I wanted to point out here to you is the 5-layer sun shield below the telescope mirror. And this is the size of a tennis court. It's really huge. And there are 5 layers. And the purpose of this sun shield is to keep the telescope cool. Since it's an infrared telescope, it has to be kept really cold. Otherwise, the infrared background will interfere with the observations. So since Hubble was in low Earth orbit, it had a tube around it to protect it from the outside light and heat. But this telescope is 1 million miles from the Earth, and the sun shield is facing the sun and the Earth. So it will block off the heat of the sun and the Earth and keep the telescope cool. So there are 5 layers which cool this. And the lowermost, and it's made out of a very thin, light, and strong material, and strongly reflective material called mylar, which is also coated with more reflective, I think, aluminum. And the lowermost layers have got further coating, anti-reflective coating of other materials. So this was a very difficult technology, and it took a long time to develop and to test. But it is now working. The telescope is in space. And also, as you can see, it is so huge. So to put it in the rocket, this had to also fold up with the telescope and then unfold like an umbrella under the telescope. So the power of the telescope is its science instruments. And it's, as I mentioned earlier, it's 5 science instruments, and each have been designed to study specific science objectives. And here is an image of the Whirlpool galaxy with a footprint of the 4 instruments in different parts, showing which parts of the galaxies will be, these instruments will be used to study. So let me just mention the 5 instruments. One is the near-infrared spectrograph, and this one is to study its main focus is to study many distant faint galaxies. And then there is the near infrared imaging slitless spectrograph. This studies the composition of exoplanets' atmospheres, observes distant galaxies, and it'll examine bright objects that are very close together. The near-infrared camera, its goal is to study the earliest stars and galaxies in the process of formation, stars in nearby galaxies, young stars in our own Milky Way galaxy, and objects from a distant region of our solar system called the Kuiper Belt, which is beyond other planets. It can also track the motion of exoplanets as they orbit their stars. The mid-infrared instrument will look at cooler objects like debris disks around stars, which emit most of their light in mid-infrared. And it will study extremely distant galaxies whose light has shifted into the mid-infrared over time. So this diagram on the right shows you, the wavelength ranges in which these instruments operate. The NIRCam, NIRISS, and NIRSPEC, they operate in the near-infrared, and the MIRI is in the mid-infrared.
Dr. Hasan, with respect to the ray diagram you showed earlier, so all four NIR plus MIR will receive light from the main mirror. All the light comes from the main mirror. Okay.
Right.
So that means,
as I showed you in this, let me just go back. See over here?
Yes.
So see this focal plane, that's where the instruments are. So there'll be,
So that means all four instruments will see the same object at the same time if needed to be.
Simultaneous observations can be done. It will depend on what is being observed, but typically the instruments will be the telescope will be pointed for whatever observation is done, and the light will be directed to the appropriate instrument.
Yes. Okay. All right. Thank you.
Yes. But there are some capabilities of doing parallel observations. I'm just forwarding. So for people who want to know a little more detail, I put up a slightly more detailed chart, which shows you, the science requirements. The camera is a wide field deep imaging camera. The NIRSPEC is a multi-object spectroscopy, which I showed you earlier. It had those micro shutters in it. The MIRI is a mid-infrared imaging, and then the fine guided sensor and the near-infrared slitless spectrograph. And then on the right-hand column gives you its capabilities. Yes, I should mention that the NIRCam and the MIRI also have coronagraphs. Coronagraphs are sort of like plates which will block off the light from the central star when you are trying to look for extrasolar planets, and you do not want the light from the star to be prominent. So you can see the planets around the stars. You use a coronagraph. And both NIRCam and MIRI are fitted with coronagraphs to have that capability. Okay. So I just mentioned the Earth's Webb's orbit. So where is Webb's orbit? It is at a point L2, which is about 1 million miles from the Earth. It's a semi-stable point where the gravity of the Earth and the Moon and the Sun kind of balance out, but it's not totally stable. And so Webb will be orbiting this L2 point, but its sun shield will always be pointing towards the sun, so that the telescope can remain cold. And so together with L2, as the Earth orbits the sun, so will Webb. It will be orbiting the sun with L2, but in itself, it will be orbiting L2. So here is just a cartoon showing you the telescope, the primary, secondary, and here is the sun shield, and this is the back side of the sun shield is shown here, the sun-facing side. It also has the steering and control at the back in the spacecraft bus, and there's a solar array at the back. And in fact, if any of you saw the actual launch of Webb, and you can go and see it, there's a recording there, you can see the solar array coming out and being deployed. And then there's a communication antenna here, which communicates with the Earth. So here's the Webb's unfolding sequence, and I will show this to you in a here's the video showing the Webb unfolding, and first. So now the mirror comes out, and then the sun shield starts opening. And after it first opens on one side, then it'll open on the other side. Then it will tighten up, it'll tension. And once it's nicely tight, then all the 5 layers separate. And once those separate, then the wings of the mirror open, and the telescope is fully deployed, and it's ready to be focused and commissioned. So all these steps have been, oh yes, the secondary mirror comes first, and then the wings get deployed. So this deployment has taken place, and the telescope is currently being, oh dear, how do I go to the next slide? Okay, so how do we talk to Webb? So I just mentioned the communication antenna. So the signal from the communication antenna is sent to what is called the Deep Space Network in Goldstone, California. And from there, it is conveyed to the Space Telescope Science Institute in Baltimore. That's where the operations center is of the telescope, and commands to the telescope again are sent from Baltimore to the Deep Space Network, which then sends it back to the Webb antenna. So that is the process for communication. Right now, we are in the commissioning process, a total of 6 months. We've launched, the sun shield and mirrors have all deployed. It arrived at L2 safely, it cooled down. The telescope alignment has started, and the instrument calibration. So we are at this stage, the alignment and instrument calibration stage. And by June, we hope to have science-ready images related, which will be released to the public and of course to the scientists, and then we'll be ready to do science. So I wanted to mention that Webb, as I said, it is an international collaboration. It involved 29 states in the United States, plus a total of 14 countries, Canada plus 13 countries in the United States. So it's a truly international mission. The road of JWST to the stars, as it started, the telescope was assembled at Goddard Space Flight Center, and then a special container was made for it, and it was placed in that container. Wasn't made in Goddard. It was actually, I think, made in Canada, and there's a special bus also, and it was placed in that container and then into aircraft, which was also the hold of the aircraft was specially altered so that container could be fitted there. And then it flew to Johnson Space Center for optical testing. And from there, it flew to California, where it was integrated at Northrop Grumman into the spacecraft bus. And then it was put into a ship, MN Colibri, and sent off to the launch site in South America, and it was launched from there. We had this beautiful, beautiful launch, and it is now at L2. And here are some fun pictures where Webb is starting its journey, loaded into that special container that I told you. It was called the Space Telescope Transport for Air, Road, and Sea, STARS. And here it's showing that Webb is starting its journey from Northrop Grumman Space Facility in Redondo Beach, California. Here it's approaching its launch site in the ship MN Colibri, and the European spaceport is in Kourou, French Guiana in South America. And the rocket was the French Ariane 5 rocket. That is the only rocket big enough for it. And the spaceport was at the right place to launch it, to put it in its orbit to reach L2. And on December 25, 2021, which is Christmas Day, we got a perfect launch, taking Webb to a perfect orbit on its way to its final destination. And here is a picture of Webb leaving the rocket. There was a camera in, sorry, was there a question?
Yeah, sorry. I wanted to ask, why French Guiana? Why not? US has got so many launch facilities and launch pads. Why go to somewhere else?
Yes, so there are two reasons. One is that the location, the latitude and longitude, and so the location of French Guiana was just right to put Webb in the orbit that it was required to be put in to get to L2 efficiently. And fortunately, at that location, European Space Agency already has a spaceport where it can launch this biggest rocket that exists, and the only one which could fit Webb into it, the Ariane 5. So that was the reason that this French Guiana was chosen, because that was the right location for the launch of this telescope. So here's another nice picture of the actual telescope leaving the rocket. And I don't have a picture, and then, just like a few seconds later, the solar array deployed, and it came down, and you can go see the replay. It's really very dramatic. It was a very emotional moment. But I personally have been working on this mission since it was first conceived in 1989, when we had the first conference. And then I was, I think, one of the first program scientists for it when it was Next Generation Space Telescope, NGST. And in fact, we were reviewing the mid-infrared instrument on 9/11 in 2001. I had organized the review, so I'll never forget that. So whenever Miri is mentioned, that picture comes in my mind.
Why does it take so long to plan? You mentioned 1989.
Well, 1989 was just before Hubble was launched, and people started thinking, what should we do next now? So scientists, they'll start thinking, what do we do next? So they had a conference in Baltimore and started thinking, what should we do next? And so that was, we think of that as the first conference. where the idea of another telescope was discussed. And then later on, NASA had its usual, what they call a decadal survey, when a committee of the National Academy is put together and looks at the science priorities, astrophysics priorities, and then they recommended this next generation space telescope, an infrared telescope. And you know, the size of the mirror changed. They said 4 meters, then the NASA administrator said go for 8 meters, and finally we settled on 6.5. And so yeah, so we call 1989, so that's when the scientists started thinking, what do we do after Hubble?
So there's a lot of discussion, a lot of going back and forth and whittling down the technologies and everything.
Right. And getting the budget. I mean, this is paid by the US taxpayer. And,
yes.
And by the Europeans and Canadians after the partnership. So first of all, we had to get the funding approved.
On the funding, is it equal tripartite, or US taxpayers hold the lion's share?
Sorry?
On the funding. Is it equal distribution, or US taxpayers hold the lion's share?
We are the US is the major partner in it. In this, it costs us $10 billion, and European Space Agency and Canadians are minor partners. European Space Agency provided the launch and one of the science instruments, and Canadian and half of another partnership in the mid-infrared instrument, and the Canadian Space Agency has provided the fine guidance sensor and one of the instruments. So they are minor partners. Yeah.
And Dr. Hasan, this picture right now of Webb leaving the rocket, if you don't mind explaining, what are we looking at? Is this the communications antenna?
No, this is just the back of the telescope. So, you're just seeing the back of the telescope.
I see, okay.
Leaving. Yeah. Yeah, the communication antenna nothing had come out. The first thing that came out was the solar array, and that came out a little later. I don't know if they have a still picture of it, but as we saw it in real time.
The video show, I saw the array coming out.
Yeah, but I don't think we saw the antenna coming out. So
okay.
So this is just, I think, the back of the telescope.
So this whole James Webb telescope is a huge exercise on folding and unfolding. How many origami scientists were there on board with you?
Yeah, I don't think there were many origami scientists out there, but we had a competition, an art competition, which a lot of really creative artists had come, and in fact we have that also on the website. The art that children did and adults did, but it took a lot of testing to do the folding, especially the sun shield. Oh my goodness, that was that was something. Yeah, I mean, to the last minute we were just sort of giving, I hope it all works. They were just like, how many parts? 234 parts, and and suddenly you have to redo the screws, and it was really very challenging. It always amazes me how these things actually work once they are there.
Yes, it does.
Okay, here are some pictures again which NASA had released of the focusing of the Webb getting into sight. So the first one on the left-hand side is an initial alignment. So you can think of it sort of like the first light, where each of the mirror acquires an image of the star, and then the second image, the middle picture is showing where the mirrors have been adjusted. So each mirror has been able to get the star at its center, and then they have been all been, all the images of 18 images have been stacked together. So this is really kind of what we call a coarse focus. And after that, they are doing more adjustments to get fine focus. And as I said, they're doing the telescopes. So what is exciting me the most that I'm looking forward is the science discovery science discovery potential of Webb. So here in this diagram, you'll see on the top are the 4 science goals of Hubble when it was launched. And in the lower side are the 4 science goals of Webb. But let's see what Hubble actually achieved. Not only did it achieve its science goals, but you see in the red, the things it achieved that we didn't even know exist, or we had very little knowledge of. Ages of stellar pops beyond Milky Way, imaging and spectroscopy of exoplanets. We didn't even know exoplanets existed when Hubble was launched. Gravitational lensing and dark matter. Nobody knew what gravitational lensing was. We didn't know if there were supermassive black holes. We didn't know what were the sources of gamma ray bursts. We learned the age of the universe. And nobody knew about dark energy. In fact, there's now even a Nobel Prize on the dark energy, which used Hubble data. So we got to know so much more from Hubble than it was designed for. So what is Webb going to find? I'm really waiting to see that, in addition to its science goals, which are amazing to begin with. What else is out there in this amazing universe of ours? And finally, the final thought I will leave with everyone is that even if you do not have an observing program on Webb, you can still analyze the data. All the Webb data, like all NASA data, will be archived. The Webb data will be archived in the Mikulski Archive for Space Telescopes. It will be available to the public. Anyone can analyze the Webb data. So you young students, Webb data will be waiting for you when you are old enough to analyze it. And here are some websites. If you want to learn more about the James Webb Telescope, please visit these NASA's websites. There's a lot of fun stuff out there, which I'm sure you'll enjoy, and you'll learn quite a lot from it. And with that, I'm ready for questions. I know there was a lot to take in this, but I hope I have raised more questions in your mind than answers, and that you are feeling excited by the potential of Webb Telescope. Thank you.
Thank you, Dr. Hasan, for that fantastic overview of James Webb. Before I open up questions to students and all, I would like to ask a few basic questions. You mentioned you started James Webb discussion in 1989. So I would like to ask this, now that Webb is up there, what is going on with scientists right now? What are they discussing?
Yeah, so what exactly is the question?
Question is, what are they discussing? What is the next thing?
That's a very good question. So as I told you that every 10 years, we get the National Academy to look at the future and tell us what to do next. So the last, and we call that a decadal survey of astronomy. So NASA and the National Science Foundation, NSF, they jointly are, because both do astronomy. And this year, even the Department of Energy joined, because they also do some astronomy. So the National Academy then tells us what to do next. So Webb was 2010, 2000, yeah. So Webb was recommended by the 2000 decadal survey. The 2010 decadal survey recommended a telescope which we now call the Roman Space Telescope, named after Nancy Grace Roman, who was considered the mother of Hubble. So we are right now constructing the Roman telescope. And we've just got the report from the 2020 decadal survey for the telescope after Roman. So that is what the scientists and engineers are now thinking about, what this next new telescope will be like. So they said basically it should be a large ultraviolet infrared telescope capable of searching for extrasolar planets. So in short, that is what the goal of that. So the scientists and engineers, this report just came out like a couple of months ago. So they're just trying to think what to do next. NASA's doing its next steps.
Yes, Dr. Hashima, if you could just stop sharing, so we could put your picture as the main picture. Yes,
Okay.
that's nice. That's nice. Now, that's nice. Okay, and who is James Webb?
James Webb was the NASA administrator. I don't remember if he was the first or the second administrator, but he was the one who saw the potential of space for doing science. So he introduced science into NASA. So but two administrators back, the NASA administrator, Sean O'Keefe, decided to name the next we used to call it the Next Generation Space Telescope. So he decided that this should be named in honor of James Webb.
Okay, all right. That's nice. Okay. I would like to call upon Mr. Amar Zafran from SK Kir Johari. Ada?
Yes.
Yes, okay. You have a question, I understand, you would like to ask?
Yes, I have a question for Dr. Hashima.
Yes, please.
In your role as a program scientist, how do you make sure that each project mission remain possible and true to NASA's strategy objectives?
Oh, wow, that's a very difficult question. So, yeah, no, that's a very clever question. So our job is basically to take the mission from what we say from cradle to grave. So how do we do that? So we, to begin with, we get a group of scientists to set what we call the science objectives of the mission. And then once those have been decided, and then we decide what instruments have to be made. So I will then write a solicitation asking scientists to submit proposals for those instruments. And I'll put together committees of experts to review those proposals, and then we select the instruments. And then when the instruments are being made and the mission is being made, we get them to report to us regularly. So we attend all those meetings. We go and visit the sites where the telescope and the instruments are being made. We have meetings with all the scientists. So at every step, we know what's going on with the mission, and we have to make sure that as it's being built, the science will be able to be done. So if there's something which needs to be changed, well, we'll say, how will you make sure that this science will happen? If they say, okay, we're going to change the shape of the mirror. Well, if you change the shape of the mirror, how much will you change? Make sure that it won't affect the science. Show us the tests. So that's how we do that. And then after the mission is launched, then we get the science proposals from the scientists to do the best science. So in a nutshell, that's what it is. But that's a very good and very difficult question.
Yes, it was. Yes, it was. Difficult question. Yes.
Yeah.
Mr. Muhammad Adam Firdaus from SK Ibrahim.
Okay, this is my question. I love space very much, but how do you know what kind of scientist you wanted to be and when?
When a scientist is one who tries to understand how nature works, and that can happen at any age. I mean, you're a scientist at your age when you start wondering, how does this work? How do I find out about it? And you start looking for ways, doing experiments and reading and researching and figuring out how to do, how to answer those questions. And so, as I said, you can be a scientist at any age, but if you want to become a professional scientist, of course, you have to go through your school and college and so on. But a scientist is basically one who tries to answer the questions of nature. You're on mute.
I get it now.
Yes. Mm-hmm.
And Mr. Tanway Jin or Miss Tanway Jin from SJKC Kuala Ketil.
Hi, Dr. Hashima. I am Binjay. Is becoming a scientist your ambition since you were little?
Can you repeat that? Do it a little slowly because I don't hear very well.
Okay. Is becoming a scientist your ambition since you were little?
Can you repeat that? I really didn't get it.
Is becoming a scientist your ambition since you were little?
Oh, since I was little, yes, it was. It really was. And I can say that a big influence behind it was my mother, who used to always say that this daughter of mine will be a scientist. And I was naturally curious also, and especially the stars. I remember I grew up in India, and the India that I grew up in was, they didn't even have electricity in most places. And so in the summer, it used to be very hot, and we used to sleep outside under the stars. And I would just stare at the star, and there was no pollution. So the skies were clear. Sometimes we used to even see the Milky Way. So I used to lie at night and just stare at the stars and wonder what they were. And my mother used to say, this is the garden laid out by God. And then I used to look at the moon. And, you know, in India, they had a little rhyme for little children about the moon. And she used to say that rhyme to me. So I was always curious about astronomy and generally about nature.
Okay, thank you.
There is a question by Prof. Hashita. Dr. Hasan, how many women scientists are directly involved in the instrument teams?
With this telescope, or?
Yes, I think so.
With this, actually, there are quite a few women scientists. The principal investigator of the near-infrared camera is Marsha Riki, Dr. Marsha Riki from Arizona State University. And at NASA headquarters, I think I'm the only one with James Webb. But in Goddard Space Flight Center, there are many scientists there, Dr. Jane Rigby, Dr. Amber Strom, Nicole Cologne. I mean, there are quite a few in Goddard, at JPL, and other places, Space Telescope Science Institute. So there are quite a few women.
There is another one in the chat session also. As a scientist, do you believe or expect to find intelligent extraterrestrial life at exoplanets?
Well, I don't know, but certainly that is a goal of Webb and of scientists to see if there could be life out there.
Could be.
And so the telescopes that we have sent, the one that is right now, the TESS telescope, is looking for what we call Earth-like planets, planets which could harbor life, whether with the rocky planets that they are not hot enough, they're what we call the Goldilocks planets. They're not too hot, not too cold, but they're just right. So if they have the right atmosphere, they have oxygen, they have water, and that's what Webb is going to look for. Then it's possible that there is life out there. And we don't know that, but we are certainly looking for it.
I suppose that's why the TRAPPIST-1 system is very interesting. Yes.
That's why that's a very interesting system. There are 7 planets there, and there's some which are in what we call the habitable zone.
A related question from Facebook. Is there life on Titan? This is because you mentioned that there are rivers, lakes, and weather on this moon. If there's water on Titan, there should be oxygen. And also are there amphibians or fish? What kind of weather on Titan?
Yeah, and we do not know those details. And we hope Webb will be able to tell us some details of that. But right now, till now, we haven't found life anywhere.
Yes.
I remember many years ago when this Martian rock, there seemed that may be life in Martian rock, but we didn't really find anything there.
Yes. Miss Nur Ain Dafina from SMS. Yeah, carry on. Your question.
Hi, and a very good morning, Doctor. So here's my question. What inspired you to venture or involve yourself into this field? And in your point of view, is this field quite difficult to be learned by the beginners?
You know, I'm having a bit of a difficulty following the question. I think the sound doesn't come out very well.
I'll repeat her question to you. What inspired you to venture into this field? And is it difficult to learn?
My path to astronomy was actually quite twisted. My first love was nuclear physics, because that's where I did my theoretical, I did my PhD in. But then life took me to other places. I got married, I came to the United States, and I came at a time where, at that time, there were very few women in science, but I was still able to do nuclear physics, and then went back to India for a short time. And then when I came to Baltimore, they didn't have nuclear physics. And there was this new institute called Space Telescope Science Institute, which had been made as a science institute for the Hubble Space Telescope, which is going to be launched. And they were looking for someone who could write the optical simulation software for Hubble and its science instruments. So I went there just sort of generally looking. I'd gone to Hopkins actually looking for a job in nuclear physics, and they said, "Oh, we're not doing we are closing our nuclear physics department and opening astronomy." And then I met someone who I'd known in Oxford, and he said, "Oh, why don't you go to Space Telescope and see if there's something you can do there?" So they said, "Well, this is what we are looking for. Do you think you can do it?" So I said, "Oh, why not?" I thought, I know physics and I know optics, I can do it. Though I'd never done programming of optics before. And so I sat down, and those days, again, the designs of the instrument, big blueprints, on paper, and see. So that's how I started in astronomy, writing the simulation software for the Hubble Space Telescope. And then I asked them, I said, I'm a scientist, I need research time. So they gave me a little bit of research time, and I started doing research in astronomy. And being a theorist, I was started doing theoretical research, and that's how I got into astronomy. So sometimes, life takes you in places, and you have to see how to adapt, and maybe you'll even get your dream. So I'd always wanted to do astronomy, and here I was able to do it.
But looks like you took a meandering route, just like James Webb.
It was very meandering. I've only told you in 2 minutes, but there was more to it than that. Yeah.
Yes, okay. But if you were to weight astronomy and nuclear,
it's like apples and oranges,
Okay,
If you like
definitely.
both, then you want to
Definitely.
eat both, right?
Okay. Definitely, I wouldn't leave both for
Yeah.
anything. Yes.
Yeah.
There's a question in the chat box. What from Arya? What do I do to be like you, Dr. Hasan?
What you do to be like me? Work hard. I don't know which part of me you liked, but if you want to be a scientist, I'd say work hard, satisfy your curiosity, pursue your passion, whatever you are passionate about. Pursue that. There will be difficulties in your path, but find ways to go around them and conquer them. And if you're still a young student, you have to work hard and do well in your studies, and also find a mentor, someone older and wiser who can help you attain what you want to attain. So that would be my advice.
Okay. Another one from Miss Awatif Kistina, SMS Sultan Muhammad Jiwa. Ada? Are you there?
Yes, I'm here.
Okay, go ahead with your question.
Okay, first of all, hi, Dr. Hashima Hasan. Okay, my question is, what will Webb telescope tell us about planets outside our solar system? Will it take photos of these planets?
So what will it tell about planets outside our solar system?
Yes.
Yeah. So that's what we call extrasolar planets. And current telescopes have been able to tell us about some extrasolar planets, their masses and sizes. So with Webb, we hope to find more of these planets, smaller and fainter planets, and above all, maybe we can find out if they have atmospheres and what they have in their atmospheres, whether they have water there, whether they have oxygen, whether they have carbon, whether they have methane. If they have methane, then certainly it's probably they have life like ours over there.
In the chat box, in your opinion, this is a bit deep, why is the study of space important to the current and future generation?
Why suddenly?
Why is the study of space important to the current and future generation?
Yeah, the study of space is, we want to know where we came from and how our universe will end will also help us with the study of space, because we know what our star, the sun is our star. And by studying space, we can see the life cycle of stars, the life cycle of something like of a star like a sun. And in that way, it gives us some idea of what our future will be like. So that is one advantage. That is one thing that I can think of that is, and of course, it's a natural curiosity to know what is there. And also when you're doing science, you can't say immediately what it is going to lead to. The scientists are satisfying their curiosity, and then suddenly, one thing leads to other. When the scientists who were trying to understand what an atom is, and look, now today you and I are talking because of all those electrons which are flying all over the place.
Yes. Curiosity and
yeah. So it's not always possible to predict the future.
Yes. Okay. Mr. Muhammad Fitri Hatim from SMS Sultan Muhammad Jiwa.
Yes, I'm here.
Carry on.
As for my question, was there any challenge, any difficulty, or any problem that occurred during the construction of the James Webb Space Telescope?
During the what? Any problem during construction? Oh yes, believe me. There was, because it's a very hard technology, and that's why it took so long to build it. The sun shield is one thing which I told you, that 5 layers, and it's got lots of little screws and bolts and nuts and bolts, and it wasn't always easy to get everything fitted just right. Sometimes a little tear would happen in the shield, then you would have to fix that. Some nuts and bolts wouldn't fit properly. You would have to redesign those and put them back. So yes, there were a lot of problems came up, some big, some small. And that's why it took a lot of time doing it, because when you're doing something so difficult and so novel for the first time, you don't know how long it'll take and what it'll take to complete it successfully.
All right. Before I go to a technical question, there's one from Facebook. This one is quite deep. Dr. Hashima, what are your biggest achievements?
What are my biggest achievements? Oh my goodness, what is my biggest achievement? I don't know.
James Webb.
Raising my grandchildren. I don't know.
I expected James Webb.
Really, raising children is the hardest thing on Earth. But yes, James Webb, Hubble was actually quite hard doing the optics that I mentioned to you, that I wrote the software. And then when Hubble went into space, now a lot of you will not even know this, because Hubble is now 30 years old. And so anyone who is, I think, below 40 doesn't even know that the Hubble mirror had a problem. So when the first images came down from Hubble, they were flawed, they were blurred, they weren't sharp. And I was made the optical, I was the top optical telescope assembly scientist at Baltimore. So they made me the optical telescope assembly scientist. They said, now you know all the optics of Hubble. Now it's your job to analyze it and keep this in the best focus that the scientists defined at that time. And so that was a really very challenging, very hard job. I had to, get images down periodically, analyze them, and then characterize the error so that a fix could be done. We had to really understand what the error in the telescope was. And then when the servicing mission was done, I was told to get the telescope in the best focus before they could deploy the corrective optics. And they said, you'll be given 3 chances to do this, and you better get it right. And I got it right the first time, but it was, I'm telling you, I was very nervous. And yeah, so that was, I would say, one of the most challenging things that I've done.
So this was software correction.
Yeah, well, yes,
Before
what
the
I did
hardware.
was, I did the software analysis, and then
analysis,
I would
okay.
tell Goddard's, they were the operation center that moved the mirror by so many microns.
I see.
So it is in the right position for the best focus.
It's essentially you were the microprocessor controlling the mirror movements.
I was kind of. Yes.
The brains behind.
it.
Yeah. All right.
Yeah.
That's nice. Okay.
Yeah.
That's nice to know you.
Yeah.
Okay. There's a few more questions here. What is your favorite part of being a scientist?
The favorite part of being a scientist is just trying to think, how do I solve this problem? And then when you're able to solve it, it's very exciting. Since I'm a theorist, I mean, I'm able to solve problems whether they're the right answer or not. I mean, the theorists come up with their theories, but it is very exciting to understand how something works, or at least make some progress towards it, to understand how it works. And that, I think, is my most favorite part. And also, as a scientist, you are pretty much in control of what you are doing. This is something you love doing, and you're able to do it. How many people are fortunate enough to do what they love doing? But, being able to solve problems and understand nature, I think I find it very exciting.
Okay. On the chat box, Dr. Hasan, why is the primary mirror made hexagonal? Why not other shapes?
Yeah, that's a good question. The reason is that these, when it's a hexagonal shape, they're able to fit in very nicely without leaving spaces in between. And you want to get a really smooth mirror, and then also it needed to be folded. So it had a two. If you had spherical pieces, then there would be holes between the two pieces. So this seemed like the best shape to give a smooth surface.
That's quite easy. The next one is, as you said, the sun shield is one of the most challenging work that had been done. Why not reuse the idea of the Parker Solar Probe sun shield design? What is the key benefit of this ultra-thin 5-layer sun shield and the difference to Parker Solar Probe sun shield?
I'm not so familiar with the Parker Probe sun shield, but I don't think Parker Probe is at a million miles from the Earth, right? How far is it? So, but this sun shield is really to protect the telescope from the heat of the sun and the Earth at the L2 position, and to keep the telescope cold. So this is a big telescope, and so the sun shield has to be large enough to keep the rays of the sun and the heat of the sun away from it. So it has been designed specifically, custom. You can say it's been custom designed for Webb.
Yes, thank you. Any questions from the Zoom participants here? Anybody? Nothing?
Yeah, I have a question.
Yes, please.
Okay, Dr. Hasan, my name is Mr. Zueli. All right, I don't know whether the question is classified or not, but then is there any upcoming project beside after this James Webb Space Telescope? Thank you.
Yeah, so the next big telescope that we are building is called the Roman telescope. And this one is actually, it's not as big as Webb. It's actually the same size as Hubble, more or less. And so that's the next one that we are building.
Okay, thank you.
Mm-hmm.
Dr. Hasan, on the chat box, what do you find interesting in space telescopes?
So the interesting thing about space telescopes is, as I mentioned earlier in my talk, that they can capture whichever wavelength you need to study something in. And so that's why space telescopes are very advantageous and good way to study the cosmos. And and ground-based telescopes have the disadvantage that you can't, if you want to see something in X-ray or gamma ray or ultraviolet, you can't do it with a ground-based telescope. So I think that is the most exciting, important thing about space telescopes. And even visible light is much clearer in space than on the ground.
On a related topic, will there be something, do you think, even remotely, that we could station something like the ISS up there that could do a whole host, a myriad of wavelength scannings and all that?
We do have, we don't anymore, but we did have a small telescope on ISS, not really a telescope, but one for, I think it was for particle physics. It collected, but there has certainly, scientists will think of everything, right? They certainly have talked of constructing telescopes in space, sending up pieces to space station and constructing telescopes in space, but nothing practical has been proposed so far. People have talked of putting telescopes on the moon, now that we are going back on the moon. So I'll certainly say people have thought about it, but I don't think we've actually come up with anything practical.
Nice.
People have even thought of robotic servicing missions or robots making telescopes in space.
Yeah. How fast? There's a question in chat box from Arya. How fast is the telescope orbiting L2?
How fast? Now that I don't know the answer to that. How fast? What speed it's going around L2 in? No, I don't know the answer to that one. That's a good one.
But it's a complicated movement, right? So it's
right. More like Lissajous figures.
And so following Earth going around. So it's actually doing a set of spirals all around
it's like Lissajous figures,
Oh, Lissajous figures. Okay.
Yeah.
That's a good one. Lissajous figures. Okay. Dr. Hasan, how far can the Webb telescope see, or to be specific, how many light years can it see?
It can go back to about almost 14 billion years. Now you can calculate the light years yourself, but it's 14 billion years. It'll be a few 100 million years after the Big Bang.
Yes. Let's closer to home, Webb and Pluto.
Sorry?
Webb and Pluto. Any comments on Webb and Pluto? Yeah.
Yeah, it can see Pluto. As I said, it can see all the planets from Mars onwards up to the and the asteroid belt. So certainly Pluto can be seen by Webb.
What do we want to know about Pluto, since we have already kicked it out of the system?
Well, what you want to know about any planet, find out the details of the surface, what there is on the surface, what does it have an atmosphere, does it have, because it's not really a planet, it's in between a planet and a,
moon.
Small asteroid. It's kind of the biggest object in the what we call near Earth objects or asteroid belt. So yeah, I'd certainly like to learn more about Pluto.
Any questions from Zoom, guys? You'd like to ask yourself? Anybody? Nobody? Can we live on Mars?
Yeah. Can we
live on Mars?
Can we live on Mars?
Yes. Almost.
I don't think so, because we haven't found oxygen there. We haven't found water there. So I think it won't be a very easy life there. We won't be able to take enough oxygen there to live there. So people are still looking to see if there are places on Mars where it will be possible to live, but right now we haven't found any.
Okay. All right. I think that's about it. Okay. About your background, Dr. Hasan, this is the actual James Webb, and
yes,
and we are looking at the primary segments, as well as the center is the secondary mirror.
Yes.
Okay.
Yeah, this is the actual telescope. And I think it's probably at Goddard, because I see the NASA logo reflected off it.
Yes, yes.
Yeah.
Okay. All right, if there are no further questions, any other questions? Guys? Zoom?
Excuse me.
Yes, carry on.
I have a question. May I?
Yes, carry on. Introduce yourself, please.
Okay. My name is Nur Anissa binti Aziz. Form 2. I'm a legit 14 years old. Form 2 student of Sultan Muhammad Jiwa Science Secondary School.
Okay.
So, as I was doing some research, there was one question that played in my mind, which is, how can astronomers know things from for certain things that only look at space from one vantage point? That is my question.
Okay, thank you. So what you want to know is how astronomers know so much about all the space and whatever we know and about what we know today by just looking at things from where we are right now?
Yes, sir.
Yeah, so that again is a very good question. The way astronomers know about anything is just by looking at the light, the radiation that comes down to the Earth from all these objects into space. So ancient astronomers who didn't have any instruments just looked with their eyes. As I told you, when I was a little girl, I used to lie down at night and just look at the sky. So the first thing, so they made observations, just looking at the sky at night and seeing, that the stars were set in patterns. They moved in the sky during the night, during the whole year. So it is really by making observations. And then as telescopes were invented, they were able to see more details and learn more about them. And as more advanced telescopes were made, they got even more knowledge. Space telescopes were made, and we got even more knowledge. So that's how you got to know. But everything is really known just by looking at the radiation, at the light, the electromagnetic radiation from these objects. The objects, as well as all the phenomenon taking place, that you're seeing galaxies colliding, you're seeing supernova exploding, you see stars being born and dying, you see black holes, all that information you get from the light.
Excuse me, Dr. Hashima. I have a question.
Carry on. Introduce yourselves, please.
My name is Adam Firdaus bin Norman Firdaus. I'm from SKI and I am year 5. How to keep the mirrors clean? As you said, there are so many debris in space.
That's a good one. Dr. Hasan?
Yes, so what was the question?
How do you keep the mirrors clean, since you mentioned the universe is full of dust?
How do I keep what clean?
The
mirrors clean.
Yeah,
The
mirrors
telescope
clean.
mirrors clean.
Yeah. No, that's a good question too. There is a lot of dust, but there's a lot of space also out there. So there isn't dust everywhere, but it's in places around there. But we do actually worry about small particles of dust and so on hitting the mirrors and damaging it. And so we have other telescopes there, and studies have been done. And so dust is collected in large quantities in certain places, but again, in space, large means it's still separated by a big distances compared to the Webb telescope, So yeah, so that's how we keep it clean.
Okay, thank you for that nice answer, for the nice question. Okay, I think we are almost done. Maybe another one or two. Is there any planet with oxygen except Earth?
We haven't found one, and that's what we are looking for. We haven't found any.
Oh, a new one just popped up. If the telescope breaks down in space, can we fix it?
The Webb telescope?
Yes, the Webb.
No, unfortunately, we cannot fix Webb if anything goes wrong, because it's just too far from the Earth. Certainly, people thought a lot about it before sending there, that can we send robots up there to fix it if there's a problem, but no, I'm afraid not.
Okay, something. This is a bit off. Okay, I think that's about it, Dr. Hasan. Thank you for that most informative expose on James Webb, and the most illuminating talk on all the technologies, as well as about yourself and becoming a scientist and all. Before we let you off, I'd like to announce one. There is a quiz from JPN Kedah at the end of this event, so students, please stay around. And Dr. Hasan, could you stay on for a bit for a picture session? So we'll ask everybody in Zoom to switch on their cameras, and we will take a small picture, and then we can wish good night to Dr. Hasan. Everybody, cameras on, please. Secretariat.
Okay, ready, please smile.
Okay. Mr. Nazri, our organizer, is there? Dr. Nazri, Mr. Nazri.
Yeah. Okay, thanks, Dr. Hashima.
Hello.
Oh, no. Hafiz Ismail is there. Prof. Riza. Oh, Prof. Chan, UTHM is also here. Sorry, I missed you. Okay. Okay. All right. With that, we come to our end session.
Okay,
Dr.
thank you
Hasan,
very much.
Okay. Dr. Hasan, thank you for that beautiful talk on James Webb and the future of space science and all. We wish you a very good night, and thank you very much.
Thank you so much. It was a real pleasure talking to all of you, and all the wonderful questions that the students asked. I think I was delighted to hear that. They were really engaged, and they came out with, I think, really brilliant questions. I think these little ones come up with the hardest questions. So
Yes, they do.
thank you so much, and I hope that all of you will become scientists, or whatever you want to do, you will be very successful in doing, whether it's science or art or whatever. So thank you for attending this.
Thanks for your inspiring talk. Yes, we wish they would become like you.
Okay, thank you so much.
Thank you. Good night. Bye.
Yeah, good night.
Yeah, Masha, Dr. Hashima. All the best.
Thank you. Take care.
Thank you, Dr. Hasan.
Bye. Thank you.
Bye. Thank you.
Bye. Thank you.
Thank you, Dr. Hashima. Thank you. Dr. Hashima.
Bye.
Thank you, Dr. Hashima. Bye.
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 Students, please don't quit yet. There is a quiz. Mr. Zuhairli from JPN Kedah will conduct this. Also, please don't forget to join us, our 5th colloquium in this series, 21st May, by astrophysicist Professor Brian Keating, University of California, San Diego. We will post the details a bit later on, but please stay on. Let's engage in the quiz. Thank you. Secretariat, Mr. Zuhairli.
Yes. Okay. Thank you, Dr. Prabha. All right. Share my screen right now. Okay. All right. So first, let me introduce myself. My name is Mr. Zuhairli from Kedah State Education Department, the Assistant Director of Pupils Talent Development. Okay. All right. So about the attendance form, okay, and the quiz can now be accessed. Okay. So this is the QR code, and the link to get into the attendance form is t.ly/FJOF. Okay, so the attendees now may scan the QR code, okay, that's been displayed right now. So we will open the attendance form from 12 March until 17 March. Okay, from now on, from 10 a.m. okay, until 17 March. Okay, so this to give a chance for those who cannot join us live for today. Okay, they still can watch the rerun. They can watch the repeat of this program. Okay, on UNIMAP's Facebook live and also from the YouTube live. Okay, so we will open it until 17 March. So please make sure that when you scan this QR code, when you or you type in the link provided here, okay, you will get into this website. Okay, so please go to here, the Pautan Kehadiran. Okay, so it's a second menu over there. Okay, besides the laman utama. So please click the Pautan Kehadiran. Okay, and then this page will pop up. Okay, so this is the Pautan Kehadiran and the quiz. So please choose your respective states. Okay, so the attendance form and also the quiz, okay, is based on the states. So please click on your respective states, okay, and then please fill in your data, please fill in your information, and then afterwards you may answer the quiz. Please make sure that you have to answer more than 10 questions correct. Okay, there's a rule over here, so please ensure that you answer 10 questions correct, and then the cert will be sent to your email. Okay, the cert of participation will send to your email. All right, so I think that will be all. Good luck to all the participants for today, and good luck for all the participants with our James Webb Space Telescope for today. Thank you. If I may add, Dr. Prabha, I'm sorry, if I may add something. Okay, all right. So this is the first phase, okay, the attendance form and the quiz will be the first phase of our competition. Okay, 200 students that got a top score, okay, will move into the second phase where there's a space telescope team about short video competition. We will carry out the second phase, short video competition, okay, and then the briefing of this short video competition and the top 200 scorer will be notified via email. Thank you. Over to you, Dr. Prabha.
Okay, thank you, Mrs. Zuhaili. Harap ada cash prize. Mrs. Zuhaili, tak ada. Okay. Anyway, please stay on a bit more. We have the QR code for University Malaysia Perlis students and staff coming up soon. Yes, it's already up. You can scan the how do I make this? Okay, UNIMAP students, on the QR code for you is on the left, and all others, including UNIMAP staff, your QR code is on the right for your attendance sheet, Google form. Okay. Thank you for joining us. Thank you for asking all those wonderful questions. We hope you will all join us again for Colloquium series number 5. Thank you and have a nice day.
Thank you, sirs.
Thank you.
Thank you. Thanks for joining us. Thanks for asking nice questions.
Thank you. Bye-bye.
Bye.
Thank you. Bye.
Bye. Bye.
Thank you. Bye.
Thank you. Bye.
Thank you, sir.
Thank you. Thank you. Please don't forget to enter the quiz, win some prizes.
Okay, Dr. Prabha, thank you so much. Good job. As always, sir.
Thanks, Mrs. Worley. Thank you.
Bye. Now can I leave?